The card forecasting method is a new method that was created specifically for the M4 forecasting competition. CARD is an acronym that's derived from the four stages of the forecast generation process: calibration, average, row, and delta. The acronym is in fact reversed, and generating the forecasts will proceed from the bottom. That is, it will start with delta. Delta is a simple forecasting method that forecasts a time series using a very robust estimate of the trend and seasonal effects. It doesn't include any autoregressive dynamics. Row, on the other hand, is a forecasting method that's built around a standard autoregressive model that possibly includes seasonalities and might be differenced in order to remove any unit roots. Averaging is used to combine the forecast from the row and delta method. And finally, calibration, which is a particularly novel step, fits a complicated model, that is a model that's more complicated than row or delta, to a augmented time series that includes the original data that's available, but it also fits it to the forecasts that were produced by row and delta that were then averaged in the averaging step. So in fact, what the calibration is going to do, it's going to fit a model to the time series x1 through xt. These are observed, but also x hat t plus 1 given t through x hat t plus cap h, the final forecast, given t. It fits this model, and then the forecasts from the card forecasting method are the fitted values of the other forecasts that were produced by the row and delta method. This is novel to me in the sense I'm not familiar with this as a technique, and it's an interesting alternative to using standard forecasts and just combining them. To get started with the card method, we need to do some preliminary steps. The first step is to decide whether to use logs or not. So you have an indicator function here. We'll have lots of indicators throughout. Indicator function with a little log sign. And the rule there is if the minimum of x1 to xt is greater than or equal to 1, then log the data. It's a very simple rule to implement. We're then going to define this variable yt, which will show up later, as a simple method to mathematically define the transform variable as either the log of xt if the indicator is 1 or the level of xt itself. But this way you don't have to worry about whether we've logged or leveled things later. The second preliminary step is to determine the order of integration. So we have this coefficient I row. I row is going to be 1 for a process that's near a unit root or is highly persistent. Rather than use a Dickey-Fuller test or some sort of formal test, the rule is just simply to use a very simple rule of thumb, which is to compute the variance of the differenced y, and to compare that to the variance of y itself with this number 1.2 that was calibrated by the authors of the method. The idea here is that if we have, say, a random walk process that's highly persistent, it is moving around, then the variance of the difference, which is just the innovation to the random walk process, should be fairly small compared to the variance of the random walk process, which of course we know diverges in large samples. Alternatively, if the series was something very close to noise, so it was like an asset return series or a sort of very short memory series, so that it doesn't actually wiggle around forever and is fairly stationary, then we'd actually take the difference of the series. We'll find that the difference of the series will have a larger variance than the series itself. This is what we called over-differencing in the course. So if you over-difference the series, you actually increase the variance. And so the unit root test is basically making a decision about whether a series has a smaller variance when differenced or has a larger variance when differenced. And again, this 1.2 allows for a mild amount of persistence in the time series. Finally, once we've actually constructed our I row indicator, we're going to define a new variable zt, which again is also defined in a very mechanical way, which just either gives us the difference of yt if row is 1, or gives us the level of yt if row is 0. And again, this is just going to simplify the exposition because zt then can be used throughout without worrying about how we started from xt and transformed it into yt and then how we transform yt to construct zt. we'll just talk about ZT as the primitive series that we're going to be interested in. Of course, at some point, we'll have to invert everything to get back to forecasts of XT, which are our ultimate objective. Continuing on preliminaries, the next thing to decide is what's known as the seasonal preliminary. This is the indicator there is IA. So to find the indicator, which is IA, which is actually going to be whether this test statistic A is larger than a critical value. So here we are going to use a formal test to actually test for seasonality. We're going to use a test that's very similar in spirit to the test that we saw in the Sarima lecture on testing for seasonality. It's going to use a slightly different construct that the authors prefer, which was done to simplify the calculation, and in many ways it makes the calculation a bit faster, which I think was often the objective, because again, they were computing the entire M4 forecasting competition with 100,000 series and many forecasts of horizons and many periods. So they needed something that actually could run very quickly. So what they suggest to do, and we'll actually use this structure a lot or refer to it multiple times throughout the presentation of the card method, is to transform the data to align it. So the first thing we do is we start with ZT in the very final position. That is the final observation there. We then go backwards in observations across until we get to M columns. So M is the assumed seasonality. We're going to focus on monthly data in the project. So in this case, we can think of M being 12. Then, once we get the 12 observations, we're then going to go to the next row, and we're going to align that. And if we just let's make a simple assumption. Imagine we had data from January through December. Then, every observation in each column happens in the same month. In fact, that's true no matter which month we actually start and end with. The other thing we know is that it just makes it very simple to keep track of where we are, because the final seasonal period will always be the last column. And so the first out of sample seasonal period will always be the first column, the second one will always be the second column, and so on. So this structure is computationally efficient, and it also sort of simplifies some of the thought process. And so this structure will be referred to throughout the presentation when we talk about seasonalities. We think about the number of rows, which is tau, defined as the floor of the sample size divided by M. There are M columns, one for each season. And one thing you notice as well, and this is a slight difference from what we saw in the Sarima notes, is that we're actually going to potentially discard M up to M-1 observations because we don't have the first row. The first row is exactly complete. That is, you stop when you run out of things. This, again, just makes things simpler because you have a regular rectangular array and you don't have to worry about sort of the fact you may be missing some values for some of the initial series. Everything has the same shape. And again, this is probably more of a computational simplicity than it is a necessity, but it's done by the authors, and I think it's a good idea here. To test for seasonality, the authors use an ANOVA test. So that stands for analysis of variance. It's actually extremely similar to the test we saw in the Sarima lectures. Here, we need to compute two statistics. The first is the variance of Z bar J. So we can see there's no I. So I are the rows and J are the columns. So these are going to be the variances of Z bar J, where first we've averaged around each column. So these are going to be, of course, the average seasonal effect. So for example, with monthly data, you'd have a Z bar for January. That is the average January effect. You'd have a Z bar for February. And then all the way through a Z bar for December. So you'd have 12 of these in monthly data. So the idea there is that if there is no seasonality, then the monthly averages should be approximately constant. Of course, they won't be exactly constant because of sampling variation, but this number should be small. The variance of the monthly averages should be small without seasonality. On the other hand, when there is seasonality, this should be different from 0. Denominator then is just the overall variance of all of the data in the matrix minus the average variance of the Z bar, minus the variance of the Z bar J's. And then finally, we have some degrees of freedom correction out front. This is very similar to what we had before. M-1, because ultimately we're testing whether M-1 terms are needed, whether we just need a constant, or whether we need the sort of seasonal dummies. We can do this test. This test has an F distribution, M-1 degrees of freedom in the numerator, and M t minus 1 degrees of freedom in the denominator. So very simple thing to do. Just spotted a slight typo here. So it shouldn't be mt minus 1. It should actually be m tau minus 1. That is, the denominator degree of freedom should be m times tau minus 1. That's because m tau is the number of observations that's in our matrix, minus m, which is the number of parameters we have in our unrestricted model, so including the m minus 1 seasonals and the intercept model. So small typo there, that should be tau. Moving on, an additional preliminary is a seasonal autoregressive indicator. So the way they define this here, again, is an indicator that's defined as it needs a few things. So first, you need to believe that m has to be greater than 1. So that is, we actually have a seasonality. If we don't find a seasonality in the data, then we wouldn't ever consider a seasonal autoregression. We need t to be larger than 3 times 3m plus 1. And then we need, finally, the test statistic, which is the key thing there, to be larger than its critical value, where we need all three of these things to be true. So these are a bunch of AND operations. So the test statistic is very simple. It's just the autocorrelation. So this is rho hat, which is the autocorrelation at lag m. We square it, and then we divide it by its variance, which is 1 plus 2 times the sum of rho I for I less than m squared. Then finally, we blow that up by t, so that if this number is different from 0, this will eventually diverge. The critical value comes from a chi-square 1 distribution. So we simply do a test statistic. The uses a 10% size. So you can think of this as being a preference towards if there's any evidence that there is a seasonal autoregression needed, then you include it. One thing the authors did, which for the assignment will be strictly optional, is they extended this in monthly data in particular. If they don't find the seasonality at the m lag, the mth lag, for example, 12 for monthly data, they also considered possibly shorter seasonalities, so 11 all the way down to 2, using a 1% critical value. That is, then they got very skeptical that there may be seasonality, but they repeated the procedure. For example, if we didn't find one at 12, what you would do is you would actually then look to find a test statistic r equals t times rho hat 11 squared divided by the sum of 1 plus the sum of rho hat squared for I less than 11. So you would compute that test statistic, compare that to the critical value for R for a 1% test. And for example, if you didn't find any evidence there, you would then proceed to do this again, which you define your test statistic, R, to be t times rho hat 10 divided by the sum of 1 plus the sum I less than 10 of rho hat I squared, and so on. You continue that until either you rejected at the 1% size or you never rejected. If you never rejected, then you would conclude that IR would be 0. But if you did find a rejection, for example, at 6, which would suggest maybe there's a 6-month seasonal, then you would include IR equals 1, and you would actually change M, and this is the important thing, you change M to reflect the value that you found through this repeated testing process. This is a sort of wrinkle they added for monthly data, and you can think of it as two things. One, it may be something like a seasonality. The other thing it does is it looks for a period that might have had a particularly large influence. For example, in monthly data, it's plausible that the last month of each quarter, that is 3 lags ago, may be particularly important, even though this isn't sort of exactly a seasonality, but it still makes sense to look for these things, and that's something that the authors did. So before we start the actual process itself, we need to construct a number of preliminary steps to decide whether we need to use logs, whether we need to have a unit root, and then to difference the data, to test for seasonal level shifts, and finally to test for seasonal autocorrelation.